In today's reading, we pick up where we left off last time. So in the previous reading, we saw how to define addition and multiplication for the set of real numbers. And we almost showed that with those operations, the real numbers are a field. We have a little bit more work to do there, so we're going to start there. And then we'll also show that the real numbers have some extra structure, that they are an ordered field, just as the rational numbers are. So I'll go back over those definitions as we're going through here. So let me remind you what a field is. A field is a set, we often just call it F, that has two operations, which we'll write as plus and times, that have the following properties. So these are both operations that take in two elements from the set and return a third element from the set. So we want those operations, we want both operations to be commutative. We want them to be associative. We want multiplication to distribute over addition. And we want there to be identity elements for both operations. So we always call those 0 and 1. Whenever we take 1 and add it to any element, we get that element back. Whenever we take 1 and multiply it by any element, we get that element back. So those are called identity elements. We haven't, strictly speaking, said that for the real numbers, but if you take the sequence of all zeros and the sequence of all ones, then those would both be, the equivalence classes of those sequences would be the identity elements. For inverses, this is how we do subtraction and division. If we take any field element, there always is some opposite, and we can just do that in the real numbers by taking a sequence that represents the real number and just negating all of its terms. So that will give us an opposite field element. So when we add those together, we get 0. And then this is the last part that we still have to finish. If we have a non-zero element, then it has a multiplicative inverse. That is, there's some other element we can multiply by this one we started with to get 1. So the theorem we're going to start out by proving is that R is a field, and we've done most of the work so far. You're going to check commutativity and associativity for some of these operations. That's not really the interesting part of the theorem, so the book doesn't go into detail, but you'll check some of those early properties in the homework, and then these others we just need. The key thing was really defining the operations. So what we have to do is still show that every non-zero element has a multiplicative inverse. If x is a non-zero real number, there exists something which we write as x to the minus 1, so that x times x to the minus 1 equals 1. The book does not state this as a separate lemma, but this is the main part of the early part of the reading for today. So let me just sketch how that proof goes. We're going to choose some representative of the real number we started with. The real number we started with is non-zero. And then there is this lemma, which we proved last time, which says if you have a non-zero element, then there is some natural number, so that given any representative sequence of your real number, there is some point in that sequence, could say m, where the absolute values of the terms are greater than or equal to 1 over n for all subsequent terms in the sequence. Okay, so eventually, so if you take a non-zero and take something which is not equivalent to 0, then eventually the terms all have to be bigger in absolute value than 1 over n. And the capital N here only depends on x. It didn't depend on the sequence that we chose. But how far out you have to go could depend on the sequence you chose. But because of that, because eventually the terms in absolute value are larger than 1 over n, only finitely many of them could have been 0 to begin with, because eventually they'll always be big. They'll always not be 0. Those early terms, as you've shown on a homework problem, don't change the equivalence class. You can play around with the early stuff any way you want, and it won't change the equivalence class of the sequence, so it won't change what real number it represents. So you can take all those zeros and just replace them with something else, say 1. And then the next step is to show that this new sequence you've created, possibly new if you had to replace some zeros, that if you take the multiplicative inverses of all the individual terms, which you can do because they're rational numbers, then that is still a Cauchy sequence, using the fact that we started with the Cauchy sequence. So the bit of algebra, you need to do that. So we're going to look at the new sequence with the multiplicative inverse terms. Take x sub j to the minus 1 minus x sub k to the minus 1. You can factor out the x sub j to the minus 1 and x sub k to the minus 1. You're left with an x sub k minus x sub j. That's the difference of the original sequence you started with. So because the original sequence was a Cauchy sequence, you know that x sub j minus x sub k, you can keep that small if you go far enough out in the sequence. And so then you want to make sure that the other pieces of this don't get too big. So here, if we write this out as a product of three absolute values, that's last factor I've just said will stay small if you go far enough in the sequence. And these other two things we don't want to get too big. And for that, we can go back again to this lemma we proved last time. So this is the second time we're using it. So we go back to this lemma, and because the terms of the sequence are bigger than 1 over n, terms of the original sequence are bigger than 1 over n in absolute value, if you take their reciprocals, and this is something we just know about rational numbers, if you take the reciprocals will be less than capital N, okay? And so these two factors, the x of j to the minus 1 and x of k to the minus 1, those can't get larger than some fixed bound. And so if you're multiplying by something that's getting small, then the original differences will get small. Okay, so that's a sketch, and then you have to put in all the quantifiers and everything, which the book does. Okay, so with that lemma showing the existence of multiplicative inverses, we now know that R is a field. We have operations of addition and multiplication with all the desired properties. Now we're going to add in the next feature of the real numbers, which is that they are an ordered field. So to go back over the definition of an ordered field, you may have read it earlier, but now we're really focusing on it. A field is ordered if we can partition its elements into three sets. So there's going to be 0, and then there'll be what we call the positive elements, and then the negative elements. And this has to satisfy the property that if you add two positive numbers together, you get something positive, and if you multiply two positive numbers, you get something positive. It may seem strange that we have to make this definition if you're not familiar with other structures. If you've taken algebraic structures or complex variables, then you've seen some fields that are not ordered. There are other fields that have the addition and multiplication properties, but are not ordered. So you may have either seen those before, or when you take one of those other classes, algebraic structures or complex variables, then you will see some fields that are not ordered. But what we're focused on is showing that R is ordered. We can define positive and negative numbers in a suitable way. And because R we've built up from Q, from Cauchy sequences of rational numbers, we're going to use what we know about the order in Q to define the order in R. What we need is a way to define whether some non-zero real number is positive or negative. So we're going to go back to this same lemma that we've already used a couple of times today. So this is actually a pretty powerful property. We're going to go back to this same lemma and say, well, if x is non-zero, there is some capital N, so that whatever sequence we choose to represent x, eventually, so for sufficiently large values of k, the absolute value of x sub k is greater than or equal to 1 over n. So eventually in the sequence, the terms will be larger than 1 over n, away from 0. Now, we're going to use the additional fact that we know that we have a Cauchy sequence, that x is represented by a Cauchy sequence. The terms we've said in absolute value are larger than 1 over n, but that doesn't say anything about whether those terms, which are rational numbers, are positive or negative. And the key realization is because they're always staying more than 1 over n away from 0, if we had positive and negative terms in that sequence, then the positive terms would have to be at least 2 over n away from the negative terms. Okay, so we're saying the lemma told us that if we go far enough in the sequence, the terms in absolute value be 1 over n, so then positive and negative versions of that would be bigger than 2 over n. The sequence we've chosen to represent x is Cauchy. So their terms can't stay some fixed distance apart. The terms, as we go further out, have to get closer and closer to satisfy the Cauchy criterion. So either, if we go further out, all of the terms will be positive and bigger than 1 over n, or all the terms will be negative and less than negative 1 over n. Okay, so now we're dropping that absolute value, and we're saying there's even more we can say. So eventually, either all the terms are going to be bigger than 1 over n, and this is assuming x was non-zero to start with, or they'll be less than negative 1 over n. That's going to be the basis for our definition of positive. So the definition of a positive number is that there exists some capital N, a natural number, and some, I haven't quite stated this definition correctly. I may have to change this. We say that x is positive if there exists some capital N such that for any representative of x, and that's what I left out, for any representative of x, there is an m, a point in that sequence, so that for all subsequent terms, for all k greater than or equal to m, x of k is greater than, not with the absolute values, but just x of k is greater than or equal to 1 over n. Okay, so eventually all the terms are bigger than some fixed positive rational number. And then we say that x is negative if its opposite is positive. All right, this definition effectively says that the x itself is bigger than 1 over n, based on a property that I'll mention in just a moment. But what this brings us to is what's called the axiom of Archimedes, or sometimes it's called the Archimedean property, which says that if x is a positive number, there exists some natural number so that x is greater than or equal to 1 over n. This seems like it's the reverse of what we said before. We said that x will be positive if there exists some n, and now we're saying if x is positive, then there exists an n with this property. The reason for this is that when we state a theorem, and this is something that you'll see different books treat differently. In a definition, whenever you see if, you typically interpret that as meaning if and only if. You're introducing a new term and you're saying this term means exactly this other property. So we say x is such and such if it satisfies property so-and-so. That's what we usually say. And what you should interpret that is we say x is such and such to be equivalent to if and only if it satisfies property so-and-so. And so that's why we can say that the real numbers satisfy the Archimedean property based on this definition, because saying that x is positive is precisely the same thing as saying that there is a natural number n so that x is bigger than or equal to 1 over n. Okay, so that's why these are equivalent, and that's where the axiom of Archimedes comes from. Basically what it's saying is that real numbers don't get infinitesimally small. We don't have infinitesimally small positive numbers. Any positive number has to stay some definite amount, 1 over n, away from 0. Okay, so if now we have a definition of positive, the thing that's left to do is to show that this satisfies the axioms of an ordered field. If we take two positive numbers, x and y, let them be represented by sequences x1, x2, x3, and so on, and y1, y2, y3, and so on, then there will exist capital N sub x and capital N sub y. Okay, so these are going to give us the bounds for how far away x and y are away from 0. And now we've chosen particular sequences, so there'll be an m sub x and an n sub y, so that if you go past m sub x in the x sequence, the terms will be bigger than 1 over n sub x. And if you go past m sub y in the y sequence, the terms will be bigger than 1 over n sub y. Okay, so we have these two lower bounds which will apply far enough out in both the x and the y sequences. All right, we want to show that the sum and the product of x and y are positive. So let's take capital N just by itself to mean the larger of the two values n sub x and n sub y. And so taking a larger n means that we're letting things get a little bit closer to 0 because we're looking at, remember, 1 over n. Then if we go past the point where both the sequence for x and the sequence for y were this definite amount away from 0, then we can say that adding x sub k plus y sub k is going to be, we know that we're far enough out in both sequences that that's going to be greater than 1 over n sub x plus 1 over n sub y. And both of those terms are larger than 1 over n, so their sum is going to be larger than 1 over n. Okay, so if you add two things larger than 1 over n, then the result also has to be larger than 1 over n. What about if we multiply them? Well, if we multiply them, xk times yk, that's going to be bigger than or equal to 1 over n sub x times 1 over n sub y. And you know that n sub x and n sub y are both less than n, so the product of 1 over n sub x and 1 over n sub y is bigger or greater than or equal to 1 over n squared. And so that 1 over n squared gives us the definite amount that the product will be away from 0. And so x plus y and x times y are both positive because we found that it's found some point in the sequences that represent the sum of the product so that the terms stay a definite amount above 0. Okay, and that's what we needed. We needed to say that we could sort the elements of R into positive, 0, and negative so that a sum and product of positive numbers is always positive. And so we have the theorem that R is not just a field, but it is an ordered field. I'm not going to go through the proofs of these other properties. They're mostly pretty short in the textbook, but I do want to state them because they will be important later. First of all, if we take two real numbers, x and y, and representative sequences for those, if we go far enough out in the sequence and we see that the x sub k is less than the y sub k from then on in the sequence, then that will imply that x itself was less than or equal to y. Okay, so if the sequences have that comparison of non-strict inequality, then we'll also get a non-strict inequality of the real numbers we're looking at. There is the triangle inequality for the real numbers, just as for the rational numbers. It says that for any x and y and r, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. I've asked you to prove the triangle inequality for rational numbers already, and so the triangle inequality for real numbers will follow from the rational number case and this other lemma just right before it. The triangle inequality can be rearranged in various ways that are useful, and so I'll call these corollaries to the triangle inequality. One says that if you take any two real numbers, then the difference of their absolute values is less than or equal to their absolute value of their differences. Okay, so in the original, the absolute value of the sum is less than or equal to the sum of the absolute values. Now I'm saying that the difference of the absolute values is less than or equal to the absolute value of the difference. You can get from the original triangle inequality to this modified version. If you start with the original triangle inequality, subtract the absolute value of y from both sides. Okay, so now you have a minus absolute value of y, and then replace x with x minus y. And so you'll get an x minus y on the left on the right, and then x minus y plus y, you just get an x left in the other term on the left. And so you have the absolute value of x minus the absolute value of y. And then I put a big absolute value around the whole thing, which the book doesn't emphasize as much, but you can do this. You can take the absolute value of the left side, and it'll still be less than or equal to the right side. And that's because you could do this in either order with the x and the y. Another variant is if you have 3 points, x, y, and z, then the absolute value of x minus z is less than or equal to the absolute value of x minus y plus the absolute value of y minus z. And this is really where the triangle inequality gets its name. If you have 3 points, you might think of this as saying the distance from x to z is less than or equal to the distance from x to y plus the distance from y to z. Okay, so you can't get from x to z faster by going to y first. Okay, so that's kind of what this says. So these are variants of the triangle inequality that are useful. And then finally, one of the properties that explains how the rational numbers relate to real numbers is what we call density of the rationals, or the rationals are dense in the real numbers. And what this says in shorthand, and then I'll read it, is that if you pick a real number, there is a rational number as close as you want. So for all real numbers x and for all natural numbers n, so this is going to give us our error, there exists some rational number y so that the absolute value of x minus y is less than 1 over n. Okay, so you can get rational numbers as close to any real number as you want. All right, so those are the properties of order in R that we need for right now. We're going to do more with these. These will show up again and again, so don't be surprised, particularly the triangle inequality. Don't be surprised to see this cropping up again and again. And so if it seems a little unfamiliar right now, get familiar with it, because we'll be using it a lot in the future. And I will stop this presentation here.